Hello, everyone. In this lecture, we'll be looking at basically dynamic relocation and dynamic memory management, how it can be done in the operating system. Specifically, we'll look into various ways of segmentation and simple paging mechanism. These two are both dynamic memory management techniques. So reading assignment for this lecture would be Dinosaur chapter 8 or Comet book chapter 13, 15, and 16. So what we have seen in the previous lecture is we saw how given C files, how compiler generates object files and how linker puts them together into an executable. And then we saw how loader loads into the memory and how operating system, like what are the ways in which operating system can manage the memory of each process. Specifically, we looked into simple uniprogramming model where operating system executes only one process at a time and the process always loads at starting at address 0, and there is only one process that will be executing on the system at any given time. We also looked at multi-programming model where there could be multiple processes in the memory at the same time. So here operating system, in order to load processes at arbitrary addresses, operating system does what we call static relocation. Basically, a compiler assumes that segment like program gets loaded at address 0 and it will generate corresponding binary. When operating system actually loads the binary at arbitrary physical address, it actually does relocation. This is static relocation. By static relocation, I mean the relocation happens only once, that is before loading the process into the before loading the program into the memory. So the relocation basically modifies the offsets, modifies the addresses by adding the starting address of the segment. So here in this case, so the address, the compiler injected address as uh, 0x30, whereas when operating system loaded the executable at address n, so it actually modified the program or rather call instruction by updating the address to n plus 0x30. Okay, this is static relocation. And we saw that the simple multi-programming model that we just saw has 4 drawbacks. Like the first one is it has no protection. So a process can access another process memory. So there is no way operating system can prevent it. And it also, this model has very low utilization because the segments cannot be dynamically relocated. So, and binary is fixed. Once it gets loaded at some memory, it's always fixed. And this leads to holes in the memory which are underutilized. And other disadvantage is there is no sharing. So different processes cannot share certain code segment or any segment for that matter. And this is very bad because as we saw, there could be all programs could be using libraries, and it's better if we allow sharing. However, in case of simple multi-programming, there is no sharing. Another problem is the segmentation, or rather in simple multi-programming, we want the entire process to be in the address space once. However, this is very, first, it is very expensive. And also this leads to underutilization of the memory because process may not need the whole memory while it is executing at any given time. Right? However, in this model, we need to load entire segment or rather entire memory of the process of the program into the memory. So these are the 4 drawbacks. And so what else can we do? So in this class, we'll be looking at what we can do at execution time. Specifically, we'll be looking at dynamic memory allocation. So here, the idea is simple. So instead of changing the address before it is loaded or at load time, why can't we change the address dynamically during every reference? That means, so anytime the address generated by the program, let's translate that address to a physical address. Okay, so let's do the translation for every address. So instead of doing at load time, let's do at runtime, when the program is actually executing. When the process is executing, let's do at that time. So in order to do that, we need support from hardware. So the kind of support we need is we need some translation hardware, okay, that is provided by the CPU or outside the CPU for that matter. So, and we should have an ability to set up this translation. Translation usually happens through tables. So operating system, or rather software, should be able to set up this translation table. And then when process executes in the CPU only sees virtual address. However, the translation hardware, which sits outside the CPU, it actually translates the virtual address into physical address, so that when the memory, like when the address actually goes onto the memory bus and it is delivered to the physical memory, that like physical component such as RAM, it is actually the physical address. And the translation between virtual address and physical address is done by this special hardware component called translation table, and operating system sets this translation table for each process. And how can, like, what are the different ways in which we can achieve translation, right? So, and okay, before looking at that, having translation hardware also makes compilation and linking very simple, because now, because of this translation hardware, compiler and linker can just assume that program always gets loaded at address 0, because anyways the address gets translated every reference, right? So compiler always generates program assuming that it gets loaded at address 0. So one way to handle translation is have to maintain base address for each executable. That means, so now operating system can load an executable at any arbitrary physical address. Okay, so and now translation hardware contains two components. One is base address, okay, that says where the executable, like the starting address of the executable. And then bound is the size of the segment. Okay, basically that means the process can only access physical memory starting from base and ending from base plus bound. Okay, now on every context switch between processes, operating system, now it also needs to do this additional update of changing the base and bound address in the translation hardware, right? So now any virtual address generated by the process, it actually, the base gets added to the virtual address, and then corresponding physical address will be used to access the memory. However, for each virtual address, we also check if it is greater than bound. If it is greater than bound, we stop the process. Basically, we don't let process access that address. This actually leads to protection that we'll see later. So in essence, this base and bound, in general, translation table provides one level of indirection, right? So instead of basically now physical address is generated by adding base to the virtual address. So, and the advantages of this simple technique of base and bound is it's simple, fast, and cheap, right? All the operating system need to do is to just update base and bound for each process. And it can actually relocate the executable to any physical address. All it needs to do is to just change the base. And the technique of checking the bound actually protects processes from each other. So if process tries to access outside its virtual address range, the translation hardware detects this and it will raise an error. That way, each process is restricted to only access physical address that belongs to the corresponding virtual address that it has access. Okay? And disadvantages of base and bound is we can still have only one segment per process, right? Because the only thing that we can do is to update base and bound, and this restricts the process to have only one segment. And this still doesn't solve our sharing problem, because now two processes cannot share different regions. They can actually share the entire segment. However, if they want to share parts of segment, they cannot share. Okay. So what we have solved using base and bound is we solved a no protection problem, because now we see that if process tries to access outside its virtual address range, we prevent it. So we solved the protection problem. We kind of solved the low utilization, because we can relocate, we can move the segment of a process to any place where there is free space, right? And still we have problems of no sharing, like we cannot share parts of the code. And again, the entire address space of the process still needs to fit in the memory. Another way that we can solve, another way to manage translation table is to divide segments into multiple segments, is to divide the address space of the process into multiple segments. What it means is, let's say we have, let's say a process can access 16 kilobytes of address. Let's say it has access to 14-bit address space. That means the starting address is 0 and it ends with 3FFF. In total, it can access 16 kilobytes of memory. So we can split the entire address space into 4 segments, each segment of size 4 kilobytes. Okay, so here the 4 segments, the first segment starts at 0 and ends at FFF, and the second segment starts at 100 and ends at 1FFF, so on and so forth. So here, one thing to note here is, so given 14-bit address space, top 2 bits indicate the segment number, whereas the bottom 12 bits indicate offset within the segment. So as you can see, 12 bits is actually the size of each segment. So the size of each segment is 4 kilobytes, right? So if we convert 4 kilobytes into binary, the number of bits needed to represent 4 kilobytes is actually 12 bits. Okay, so given an address and given 14-bit address space, and we have 4 segments, each of size 4 kilobytes, top 2 bits indicate segment number, and bottom or the rest 12 bits indicate offset within each segment. And now with multiple segments, translation hardware is actually a table. So here we have one entry in the table for each segment, right? And this also provides us additional mechanisms through which we can actually set up permissions for each segment. Since each segment has different entry in the table, we can have different permissions for each segment. And now operating system has to do more work. Instead of just base and bound, it has to save the entire translation table. Okay, and it has to, every time process context switches, it needs to reload the segmentation table, like the translation table of processes. Yeah, let's look at an example. So here we have 14-bit address space, and we divide that into 4 segments, each segment of size 4 kilobytes. So here the top 2 bits indicate the segment number and the bottom 12 bits indicate the offset. Okay, so here we can see the translation table contains 4 entries, for 1 entry for each segment, and the base indicates the base address of that segment, and the bounds indicate the size of the segment. Okay, and RW are permission bits if there are 2 bits, and if the bit is set, that means that permission is allowed. If the bit is not set, then that access or that permission is not allowed. For instance, the first entry uh, is for segment 0, and the base is 400, and the size is 4b0. These numbers are in hex, by the way. And then the permission says RW. That means process can only read any address within this segment. Okay. If process tries to write to this address, then the translation hardware raises an error. Similarly, the data segment is mapped as read write, and heap segment is mapped as read write as well. And the third segment, the last segment, is unused. That means we don't we did not map any physical segment to this corresponding virtual segment of the process. So that means if process tries to access segment 3, we will fault, or like translation table will raise an error because there is no corresponding entry, or rather the entry is invalid. So now let's see an example. Now if process generates an access to address 01F4, so what happens is, as we know, top 2 bits represent the segment number. We use that to index into the translation table. So this 0 indicates the first entry. So here we take the base 4000 and we take the offset, which is the bottom 12 bits, and we add to the base that we got from the translation table, and the actual physical address would be 41F4. Okay. And note that we also check 1F4 is actually less than 4B0, because we also need to make sure that the address is within the size of the corresponding segment. And similarly, when process raises request for 15DC, segment 1 gets accessed and corresponding base address gets added to the offset, and the physical address that gets generated is 05DC. Okay. And this actually allows 2 processes to share code segment, because now the memory is divided into multiple segments. Different processes can have their segments mapped to the same physical segment. Okay. Here, what happens is in process A and B, like so the slide shows the translation table of process A and process B. So here we can see that different segments that belong to process A, specifically segment 0 of process A and segment 2 of process B, they both are mapped to the same physical segment, which starts at base 4000 and has bounds 4B0. Okay. So this could be the code region. This could be the code of library. Now we have only one physical copy of the library in the memory, which is used by both process A and process B. Right? This allows very nice sharing of code between multiple processes. So not only 2 processes, we can have several processes all having their different segments mapped to the same physical segment. And what are the pros and cons of the segment? Of course, like it allows nice sharing of memory regions. And now segments can be assigned, moved, or swapped independently, right? So instead of moving the whole segment, we can actually move different segments, because the whole address space is now divided into segments. We can actually move segments at more fine-grained level. The disadvantages is external fragmentation. This also happens in base and bound scheme. So external fragmentation means there are many holes in the physical memory, which are like there could be many small holes, but if you combine them, the memory could be larger. For instance, let's say this is an example of external fragmentation. So here you can see there are 2 holes, and segment 4 cannot be stored in either of these 2 holes. Okay. However, the total available memory is enough to store segment 4. So this is called external fragmentation. The main reason for external fragmentation is because processes can have segments of different sizes, right? So I can have I can have segments of size like 12 4 kilobit size segments. Another process can have segments of like 2 kilobytes. So there is the segments can be of different size, and each segment now has to be allocated contiguously. That also leads to, if a segment is not utilized fully, then we may have holes there. So in the next part, we will see how we can solve the problem of external fragmentation.